Yeah, ECBC has been in additive manufacturing for quite a while. In 1989, we got our first SLA 250, which is a machine that was sold by Chuck Hull and 3D Systems. It was probably the second or third system that 3D Systems put out. Very interesting machine. Chuck Hull, by the way, also invented the STL file format, which is ubiquitous across all 3D printing. That is the computer file you use to 3D print from. Just a little side note on that. There was always a little argument within the additive manufacturing community whether STL stood for Standard Tessellation Language or just simply stereolithography. So I met Chuck Hull and asked him, and he said it stands for stereolithography, just so you know. 1995, ECBC, we required our first FDM machine, which is the standard extruding thermoplastic. We moved on from there. We expanded SLA. We got into SLS, selective laser sintering. 2008, we got a polymer jetting machine, an objet machine. In 2011, we've got the direct metal machine. 2012, we expanded to desktop SLA and FDM because there was a lot more we could do with desktop SLA and FDM as far as dialing mechanical properties and experimental materials. 2015, we opened a center-wide makerspace. So anybody who works for ECBC can come into our lab and use our facilities. We teach you CAD, we teach you 3D printing. So if you have a small project, you need a bracket to hold a test tube in the hood, you can come in and we'll help you design it, and you can actually go and 3D print it yourself. So we actually train you on machines, we train you on CAD and everything else. This last year, 2017, we acquired the Carbon DLS. It's direct light synthesis. It was formerly known as CLIP. It's a really fast SLA machine, very cool machine. I have some parts around here if you want to see those. And this year, in partnership with ARL, we're installing a laser deposition metal machine. So this sprays 4 concurrent jets of metal powder into the focal point of a laser beam and basically builds up welds of metal and builds a near net shaped part that you then have to go and machine away later. So at ECBC, it's all about applications now. Everyone's talking about the future of additive manufacturing and how it's going to change the world. It's been changing the world since roughly 1984. ECBC, we focus on how we can get this technology and use it now on applications for the war fighter. And there's just a whole plethora of things that we've been doing over the years. And I'm just going to go through some of those projects and some of the applications. And you might think of, there might be an application out there where you're like, I never thought of additive manufacturing being used for that. So one thing we do a lot of is 3D data capture. It's kind of goes hand in hand. It's the washer and dryer of additive manufacturing. You've got 3D data capture and additive manufacturing. We've had a creator with Paul Reed Smith guitars for almost over a decade now. And a few months ago, they came in and said, listen, we got Peter Frampton's guitar that he used in the 70s. This is the original guitar that Paul Reed Smith handmade for Peter Frampton. We want to make a line of guitars based off of that, so we need the data for it. So they brought in Peter Frampton's guitar, and we scanned it for him. And of course, with that comes, you get the file so you can print off your own Peter Frampton guitar. This one doesn't play. But I can pass this around, so if you want to get a look at what Peter Frampton's guitar looks like, it's right there. So lots of fun stuff. We do a lot of different scanning. We work with CT data as well. There's a part back there. It's a rabbit head that we're using to take the rabbit part out of any kind of aerosol testing and put a rabbit surrogate in there. So if you look at that part, you can see the nasal passages and the esophagus and the trachea of this rabbit. And we can actually hook it up to a machine and mimic what a rabbit would be doing with breathing, but not using a rabbit. But that part's back there. With the University of Delaware, we're working on an ankle-foot orthotic. These orthotics tend to wear out. They need to be adjusted constantly, and right now they're one size fits all. So with this technology, you'd be able to, again, scan someone's ankle, their calf, and customize this directly for a person and 3D print it out. It cuts costs dramatically. This is made out of polycarbonate. So this is it's a little washed out there, but this is this ankle-foot orthotic on a custom-made machine. They want to get into carbon fiber-filled nylon as the polymer that they're using. So we needed a larger machine that we could run experimental material on. So we have other FDM machines, but they're kind of locked out material-wise. You can only use material that's sold by the company that makes the machine. So we knew a guy in California who runs a little 3D printer company called PrinterBot, and said, what would it cost to make an FDM machine for us this big and that big? And he said $5,000. And we said, great. So University of Delaware paid for that. It's in our lab, and it runs experimental material. So it's been fun to play with that one. We also do other work with other government agencies. And I think I'll pass this one around too. I'm going to take the pipe out. Excuse me. So we work with alcohol, tobacco, firearms, and explosives. So they had a problem where they have this pack of gear that weighs an ungodly amount for taking care of pipe bombs. And they used to have this rig that they would have to set up, and it just took forever, and they had to carry it out in the field. So they shrunk this big 100-pound rig down to this. So this whole disc is selective laser sintered. It's sintered nylon, some metal parts. They can put this on a pipe bomb with a robot. They can wrap some ropes around this like a pulley, and from about 30 feet away they can spin the end off of a pipe bomb with these jaws. It's pretty cool stuff. We've made about 50 of these, and these are now part of a bomb squad's pack. So they can use this instead of 100 pounds of gear. That's about 2 pounds worth. So here's some parts from Makerspace. Some interesting ideas came through. First one would be the stamper here. So we have a lot of people drawing lines of bacterium into Petri dishes. And they're doing hundreds of Petri dishes, drawing individual lines with a little pipette. So they thought, hey, wouldn't it be great if we could just stamp lines into a Petri dish? So here's a well where you put your bacterium, and there's the stamper, and you just stamp it in your Petri dish. So now they can stamp out Petri dishes way faster than they normally would. And I'll pass this one around too. Just get some out of my hands. The other one is a new container for irradiating anthrax spores. They had problems with this container, but also they had no way of figuring out where the vials of anthrax spores were in this container. Where they are located in this container determines how much radiation they get. So they would pack them in with paper towels and just kind of hope for the best. So they came into Makerspace, and we developed this lovely insert that goes into this new container. It clocks in there. They can map exactly where the vials are, so exactly what dose of radiation each vial is getting. They sent it off to NIST, and it's now a new national standard for radiating anthrax spores. So this is a very early prototype. This is FDM. Again, it's all about applications and how we can use this right now. Again, we're big on partnerships. National Air and Space Museum. I've been a volunteer with the National Air and Space Museum for 8 years now. They came to me, and they've been coming to me for years actually, and they were saying, we wish we had some kind of tactile model for visually impaired visitors, something that people can touch. So they redid their entire front gallery, the main gallery as you walk into the National Air and Space Museum in DC, and they actually put money in to get tactile models, not just something they would pull out when a visually impaired visitor would show up, but an actual model that would be there all the time for 7 million people a year. It's the most visited museum in the world. 7 million people a year, we're going to touch these models. So these are run in SLA, which is the very early 3D printing technology Chuck Hall developed. They were sent to Repliform, which is south of Baltimore here, and plated in nickel, very thick nickel. So these are now installed in the National Air and Space Museum, and you can go in and you can touch them, you can look at them. Some of them have moving parts. This is Spaceship One. The wings move on it. This was just an early prototype just to make sure we were on the right track with the Smithsonian. So Army Research Lab, we work with them quite a bit. And they had this head that they needed that they could put 4 sensors in, put a helmet on it, and then blow it up. They needed 5 of these. And they needed to have a skin on it. So we 3D printed a skull out of polycarbonate. We 3D printed the mold. The mold is in the back there. Put the skull in the mold and cast silicone around it. And we came up with this lovely head here. It's got all these holes in it for these 4 sensors. This one's a dud, and I don't know if I'll pass this around. It's pretty heavy, but it's got a lot of tears in it because this one's stuck in the mold. A lot of our demo parts that we have are duds, are the ones that didn't go to the final customer. So it was an interesting use. It was only 5 parts, and they got their testing done and worked very well. Deep Purple is a UAV platform developed in conjunction with DITRA, and that's the final bird right there, at least in its current configuration. And it was developed exclusively with additive manufacturing. Most of the parts on this bird could not be produced any other way, especially the arms. And a lot of you have arms on your tables. The arms were built, also they were engineered with crumple zones. So this one's been smashed. So it's designed to break right there. So you save your propellers, you save those very expensive outrigger motors, and it'll snap off there with a certain force, a certain load. And these are selective laser sintered. These are nylon arms. And the shell is SLS, and that has an acorns pod underneath it, which is a sensor array that we can attach to this machine. All 3D printed. And again, we couldn't produce this any other way, and it's the quickest way we could iterate this machine. This machine's gone through, gosh, 5 or 6 different iterations, and all very, very quickly. And every iteration has been lighter, it's been faster, and we couldn't have done that without additive manufacturing. I'm also going to show one of my favorite parts. So we have the carbon machine. So here's one of the arms for Deep Purple. The carbon machine's fun because you can mix the materials together and color match, but that's kind of boring, so why color match when you can just put it in the tank and swirl it up? So here's where we get into, we're running parts, end-use parts, and so it's where we're getting into something you might not have thought of. So this is composite tooling. So this is water-soluble plastic. You wrap it in carbon fiber, you cure it, you cut a section out, and then you dissolve the plastic away. So it becomes a core that you would wrap carbon fiber around. So it's a sacrificial tooling. And then rapid tooling. We do a lot of rapid tooling. Print it out on the object machine, put it in the injection molding machine, and we can injection mold parts, anywhere from 50 to 100 parts, depending upon geometry. So another thing that we're doing is we're working with PM Scott on their MWMSS, which is a mobile machine shop, and they're actually fielding 3D printing and scanning in the field. We're doing a lot of training. The machine running in the back is the TAS-5, which is the machine that they're deploying currently, and ECBC Makerspace. So again, what if we can make additive manufacturing accessible to everyone at ECBC? So it's open as long as our lab is open, and the main thing is accessibility. We didn't want people to make appointments to come in. We didn't want them to have to schedule anything. If they've got time to come in, they can work with us on that. Here's equipment that we have available to the makerspace. So we have all of our fused deposition machines, stereolithography, lots of Stratasys machines, which are the higher end machines. Next one. And then this is the equipment that's available, but they're not allowed to run because of mostly safety. So it's the direct metal laser sintering machine, a lot of the SLA machines, the laser cutter, a lot of the higher end machines. We run for them. They don't get to actually run those. There's no silver bullet. Each process provides a solution for each unique application. The silver bullet is knowing which process to use for your application. So that's all I got.